For this problem, we're going to look at a case where we have the torque, and we are looking ultimately for the time it takes to reach a certain angular velocity. So there's two parts to this. So over here, note that we are not given the angular acceleration. So we have to use the torque to find the angular acceleration. The torque is I alpha, where I is the moment of inertia. Now we're going to model this as a uniform rod about its center of mass. So I is 1/12 ml squared, so 1/12. The mass you see is 40 kilograms. And the length we know is 2 meters. Okay, so when all is said and done, it's 13.3 kilogram meters squared. So my torque is 500 Newton meters, is 13.3 kilogram meters squared times the angular acceleration. The angular acceleration is 37.5 radians per second squared. Now if I have this is a case of constant angular acceleration. I need the time. What do I know? At startup, okay, the angular velocity is 0. And at the end, what we need to figure out is the angular velocity at the end of that in radians per second. So I know that it is 2,000 revolutions per minute. Okay. This is one place where using the traditional unit conversion method works well. I convert 2,000 revolutions to radians by noting that there are 2 pi radians per complete revolution, and every minute has 60 seconds. So when I do all of this, I find that it is 200 pi over 3 radians per second. And you can plug it into a calculator if you wish. I'm just going to leave it like that for now. So we have this, and the initial, and also the initial angular velocity here. So we're going to use our equations for constant angular acceleration, and one that's most obviously going to be used. This omega is omega naught plus alpha t. Omega here is 200 pi over 3 is 0, because that's what we start with, plus 37.5 t. And if I punch all of this into a calculator, I find that the time is 5.6 seconds.